Good morning, physics students. It is Friday. Hey, 3/27/20. So our goal today is to work some practice problems. Yesterday I asked you to do some problems. I had showed you some samples. I asked you to work through them. For the problems from that page 85, there are solutions written out, worked out. If you go to your class webpage, you can check your solutions, check your work against mine, see where you're at. I don't have solutions currently posted for the page, was it 65? 63, 65, whichever it is. I plan on trying to get some solutions posted out there for you to check your work. Those problems yesterday were all fairly basic problems, so I want to just work through two samples today with you. Keep it shorter. Yesterday's video was long. Two samples of slightly more involved problems. And I forgot. Nope, never mind. I was thinking I needed my textbook, but I had typed a problem in here. So we're going to go page 63, number 7, and we're going to work this out as a sample. During a throw, a baseball pitcher exerts a force on the ball through a distance of 3.2 meters. Now, I'm not much of a baseball fan, but if you have watched baseball, a lot of those pitchers are quite tall. And so if you can imagine when they have the ball and they're reaching from way back here and extending through way out over here, we're talking a pretty good distance there. So in this case, 3.20 meters before the release. If the 0.12 kilogram ball leaves the pitcher's hand with a speed of 35.0 meters per second, how much force did the pitcher apply to the ball? So when I'm looking at this, there's my question. I'm looking for the force. I could identify things I know. I've got a speed of 35 meters per second. That's when it's leaving the hand. And that's significant because that's a final velocity. And then my physics intuition kicks in and says, oh, what was the initial velocity? Well, when the ball was back here, before the pitcher starts accelerating, the ball was at 0. So we know an initial velocity and a final velocity. Here's the final velocity. We also know the initial velocity was 0. We have a mass, 12 kilograms, so we have a mass of the ball, and we have a distance, okay? So, what am I going to try to get from that? If I'm looking for force, so think about force. What we know about force, the main equation is force equals mass times acceleration. I know the mass, I don't know the acceleration, but now again, your physics intuition kicks in and says, oh, I have this distance and velocity information. I can probably get an acceleration from that. I have to think about my equations. Now, normally in class, we point up at the board. I hope that you have written it down. If nothing else, you should have lots of sample problems written down in your notes, and you should be able to write these equations down for yourself. And I'm saying that, realizing that some of you don't always take notes the way you're supposed to. So let me go ahead. I want to make sure you have your equations. VF equals VI plus A delta T. Delta D equals VI delta T plus 1/2 A delta T squared. VF squared equals VI squared plus 2A delta D. If you do not already have those written down, please write them down on a piece of paper in your notes. Keep them handy for yourself when you're doing your work. That includes, I've always had those available on the board when we were doing tests. So that piece of paper with those equations can be available to you when you're doing tests. That doesn't mean you get to write a bunch of other stuff on there, okay? But you may have those equations. Yeah, I'll do some more thinking on that. All right, so F equals MA. We need to find the A, and so I'm going to think about my equations here. I know VF and VI and the D. So it looks to me like our equation we want to use is VF squared equals VI squared plus 2A delta D. Okay? Now I got to rearrange that. So the first thing I got to do is get rid of this VI squared. I got to subtract that from both sides. So VF squared minus VI squared equals 2A delta D. So now I got to divide by the 2 and the delta D. So I get A equals VF squared minus VI squared over 2 delta D. And I'm ready to plug in my numbers. VF squared is 35.0 meters per second squared minus VI squared, but VI squared is 0, so really I can forget about that whole term because subtracting 0 doesn't change it. That makes everything look a little bit simpler. All right, then we're dividing by 2, and I'm just going to separate this so that we've got room for our terms, and delta D is 3.20 meters. If I look at labels, this is meters squared per second squared, and I'm dividing by meters, so one of the meters is going to cross off, and that's going to leave me with meters per second squared, which is an acceleration label. Let me extend this page a bit. So, my math, I'm going to take 35 times 35, so that's 35 squared, divided by 2, and divided by 3.2 equals my acceleration is 191 meters per second squared. Now, pitcher accelerating a ball, I'm guessing is going to be a very big acceleration. But I'm going to double check my math because it does seem very large. Yep, I don't see a problem with it. So 191 meters per second squared. Sounds like a huge acceleration, but think about how long it takes for the pitcher to release the ball. It's probably just a small fraction of a second. So it's not like it's going, you know, some of these pitchers can do 100-mile-an-hour fastballs. So there is a huge acceleration in a very short period of time. Okay, with that, I'm just going to keep extending my page. I'm going to go back to my equation, F equals ma. And now I have my A. So my mass was 0.12 kilograms. And we're going to multiply that by 191 meters per second squared. And we look at our labels and say, what is a kilogram times a meter per second squared? That's a Newton. And 0.12 times 191, 22.92. We only have two figs right there, so 23 newtons. That's what the pitcher exerts on the ball. In the end, that seems like a really small force. I want you to think about that. I haven't been in a weight room in a while, maybe you can tell. But I'm still pretty confident that, you know, you could go down in the weight room and you could put easily 700-800 newtons, probably more, on a bar. You can figure out what that would be. And I can apply 800 newtons with these two arms. So that means I could certainly apply 400 newtons with this arm. So could I go out there and start pitching a baseball like, you know, a ball that no one could ever hit? Because if I can apply 400 newtons to that ball, boy, you know, that's going to be a tremendous acceleration. No one's ever going to hit that. The problem is when you start applying a force, the object is moving away from you, and now you got to try to keep up with it to apply your force. And so it's not about the force I can apply, it's how fast I can move my arm. I can't apply that force fast enough, so no, I'm not going to be a baseball pitcher. I'm not going to be able to throw a fastball that no one can hit. So one more time looking through it. I didn't draw a picture with this one. I do like to draw pictures with most of my diagrams, but to me, I guess I could have. But I kind of reasoned it out here with my velocities. I am definitely showing my work along the way, and that's what I expect from you. We're going to do one more together. This is from that other page, page 85, number 6. A 146 Newton force is used to pull a 350 Newton wood block at a constant speed by a rope making an angle of 50 degrees with the floor. Find the coefficient of sliding friction. So we're looking for mu. We know the force, this right here, a 350 Newton wood block. Newton is a unit of force. In this case, that's the weight of the block. So FW. And we got an angle. Oh, look at this. Constant speed. That's important. So I am definitely drawing a little picture of this one. Here's my floor. Here's my block. There's my force. Okay, I know this force is 146 newtons, and I know this angle, I should have drawn it a little bit bigger, is 50.0 degrees. Okay. I need to draw in my other forces. Okay. The weight is 350 newtons. Now, of this force, part of it is going this way. I'm going to call that F sub H, and part of it is going this way. I'm going to call that F sub V. Also, there is going to be a normal force, which is going to make up the difference between FV and FW because the block's not sinking into the floor. And I can tell that FV is going to be less than FW, so the floor is going to have to push back a little bit. Now, it's at constant velocity, constant speed. Constant speed means no acceleration. Constant speed means the forces have to be balanced. So what's balancing this force here, FH? There must be friction going backwards. And if it's at constant velocity, I know that the force of friction is equal to the horizontal force. Now that's important because I know that mu is going to be calculated by my frictional force over my normal force. So I have to find my frictional force. And I have to find my normal force. The frictional force is equal to the horizontal component. Oh, I can find the horizontal component. That's just doing a little trigonometry. So let's see. If this side is adjacent to the angle, and I know the hypotenuse, I want to use my cosine. I could say that cosine of 50 degrees equals adjacent, which is FH, over hypotenuse, which was 146 newtons. So FH is 146 newtons times the cosine of 50. FH equals I got the horizontal component at 93.8 newtons. You can almost guess that we're going to need the vertical component, so I'm just going to say FV is 146 newtons times the sine, because I always know that the horizontal and vertical are opposite functions, cosine and sine. Sine of 50. So FV is 112 newtons. Okay. So let's take a look at what we have now. To find mu, I need to know the frictional force and the normal force. Because the velocity is constant, the only forces horizontally are in this direction, the horizontal direction, are the horizontal component of the rope that we're pulling and friction holding back, and they have to be equal to each other. So when I calculated this, I can say that's also the friction. I got the frictional part, so I have that. The normal force. Okay. I have to have my forces balanced in this direction. So we can reason this out and say, from a magnitude standpoint, the upward forces, which are the normal force and the vertical component, have to equal the downward forces, which is the weight. Now, I just figured out my vertical component and I know my weight, so I can find my normal component. I'm going to extend my page a little bit here. My normal component is going to be my weight minus my vertical component. So my weight is 350 newtons minus 112 newtons equals 350 minus 112, 250, 240, 238, but with sig figs now we're going to be 240. Okay. My normal force is 240 newtons. So what we're saying is the block weighs 350 newtons, but the rope is pulling up-ish. And so that's reducing how much weight is on the floor by 112 newtons, which means that the floor only is pushing back with 240 newtons. Okay? All right, let's finish her off. Mu equals the frictional force over the normal force. So we determined that the frictional force was 93.8 newtons. My normal force, I'm going to go ahead right now and use the 238 newtons in here, but remind myself that that only has 2 sig figs, and I'll round it off to 2 sig figs at the end again. 93.8 divided by 238 equals, and our coefficient 0.39. So it starts looking a little bit more involved. I like it. It's starting to look like a physics problem. Because what we have to do is take all the pieces that we've learned. In the previous problem that I did, we had to use our past knowledge about acceleration math to combine along in with Newton's law. In this one, we had to use some of our trigonometry and our component concepts along with our balanced forces concepts to get to our solution, along with, what is friction? How is friction measured? What's the coefficient of friction? So, to me, the problems are getting more fun. To give you something to think about, something to process. That also means you can get stuck once in a while. Now, when you get stuck, what do you got to do? When you get stuck, you need a push. I've given you my phone number. I've been watching my email, most of the day. I watch the Google Classroom a good share of the day. If you have a question, I will try to respond. I have suggested to some of you to actually let's do a Zoom conference so we can do a face-to-face chat over your devices and look at some of these things. I was experimenting last night, and I set up a Zoom conference trial where I had one. I was using my Chromebook to show me, and I had my camera on my phone, looking at my work surface so that I could draw and write and talk to somebody at the same time. So I'm trying to be prepared to do that. So if you're stuck, ask. These are the first of the more complicated problems that we're trying. You need to open your brain, think about it, process things, go back. Now you got this on video, you can watch it through 2, 3, 4 times and say, oh yeah, that's how Mr. Up made that jump right there. Please, I'm going to assign you a couple problems to work on that are, getting to a little bit more involved. You need to put in a good effort to it, and you need to say when you're stuck and you need help. Okay? Have a great weekend. Enjoy today if you get a chance. It looks nice out today. Tomorrow is supposed to be rain out, so I'm hoping to cook some sap. I guess I have to try to stay dry. Stay safe.